Welcome. Are you able to hear me, guys? So, I hope you are able to hear me now. So, our session is live. Okay. So, in the last session, we have discussed about the wave function. So, from there, if you have any doubt, please let me know. My voice is coming to you clearly. Please comment those who have joined. Welcome, Shantanu. Very good evening to all of you guys. Welcome, Lalit. So, this is lecture 2 on our course on quantum mechanics. So, लास्ट क्लास से कोई डाउट है, कोई क्वेश्चन है तो आप पूछ सकते हैं. ओके, so I will wait for 1 or 2 more minutes so that other student can join. Then we will start. In the meantime, you guys can ask your doubt and questions, anything quickly. Please comment those who joined so that I can see who have joined. Okay. Who else is joined? Quickly comment. So today we will start with wave function in position space and momentum space. This will be the initial topic. So now I think we can start this topic. It's already 2-3 minutes. We can wait 1 or 2 more minutes. So first we have position space. So I'm writing it as x space and momentum space as p space. So as you all know very well that a wave function need a dimension with time also. So if we are in one dimension, we need x and the time dimension to describe it. So here a exponential iota kx minus omega t will be the representation of wave function in the position space. So similarly, if we need in momentum space the wave function, then it will be denoted as phi pk. So this is basically the conjugate pair of the position space. Welcome Kausiki Sinha. Very good evening. How are you? So Any question if you have, Lalit, Kosiki, Santanu from the last sessions, you can ask. We will discuss. So now this is basically the conjugate pair. So here if we have iota, this will turns out to be its conjugate pair. So here we can have a exponential of, instead of iota we will have a minus iota, and kx, here you have an omega t. So this we can keep as it is right now, and now we have to convert into the p and k form. So how to do that? So we can simply take, division of h cut here. So if I do that, what I will get, h cut k will become p, division and multiplication of h cut basically. So, and omega with h cut will give you energy t. So this will be the format in the momentum space of the wave function. Very important. So sorry, here it will be t, pt, not k. Okay. Any question till this point? It's very easy. I hope it's clear for all. So now you know very well that P is equal to h cut k and energy is h cut omega. Simple relation. If we now see a very interesting thing, which is the operator form of momentum and energy and position also in x space and in p space, then what will be the notation of that? So if I write the p operator in the position space, energy operator, and also the position operator itself, xop, op is standing for operator. Similarly we will do for the momentum space. So first, you know very well that this is given as h cut over iota del over del x. Energy in terms of t, so iota h cut del over del t. This is very well known. And x operator, because this is a x space, so its value will not change, it will just remain x. So there is nothing to do with x operator in the position space. But when you go for the momentum space, here p operator will remain itself as p, but x operator now it will change. So what will be the x operator in the momentum space? So that will basically, here this will exchange, here you will get a conjugate pair obviously. So h cut upon iota will turn out to be minus h cut upon iota, and del over del x here you will replace as del over del p, because we are in the momentum space now. So position operator will be defined, and energy operator also will be changing with the negative sign, because of the momentum space is the conjugate pair of the position space, and p operator will remain itself as p. Okay, so till this point if you have any doubt you can ask. Now we will discuss the Schrodinger's equation. We will basically have the discussion that how we can get Schrodinger equation. So we will derive the Schrodinger equation shortly with the quantum postulates. So who is joining now? Quickly comment down so that I can see who is joining. Just someone is joining quickly. Comment down. Those who are joining new, please comment down so that I can see. So now write down the heading quantum postulate. Quantum postulate. So there are few formulas which are very well known to all of you guys that we also discussed in the last slide. E is h nu, or h cut omega, and momentum is your h cut key. So how we can represent a wave function if it is a electromagnetic wave is propagating in x direction, then how we can represent a wave function that we just discussed in the last slide also. So if any electromagnetic wave propagating in positive x direction in momentum space, in x space, position space, so how it is represented? As in one dimension it will be psi xt. A plane wave representation need the dimension and the position dimension like x, y or z, and the time dimension also. So both things are required. So if someone asks you that what is a plane wave, so this should be your answer. Okay, so as we just discussed about the operators, so no need. P operator, E operator also you can write here. For 3 dimension, what will happen? X will replace with R, exponential of iota k dot R with omega t. So now this time, what will be the operator form in this case? H cut over iota was there and del over del x was there, as we seen in the last slide. So instead of now del over del x, we will have del over del x, del over del y, del over del z. All these things will be there. So in that scenario, we can simply use operator del. For energy operator also, we can have iota h cut with del, and position, which is r, will remain as r. So this is the simple quantum postulate that we can represent a wave function or electromagnetic wave propagating in position space. If it is in 1D, we can represent it as like this. If it is in 3D, we can represent it like this. So now that how we can get the Schrodinger equation from this? Can somebody tell me how we can get the Schrodinger equation from here with the help of these simple postulate? Any idea? How we can get the Schrodinger equation? Schrodinger equation is also based on these postulate basically. There is no proof of Schrodinger equation. It's just a postulate. Can someone mention in the comment box? Quickly. Okay. So you all know the total energy. It's okay if you don't know. Total energy H is given as T plus V, and obviously you have kinetic energy and potential energy. Addition, you get the total energy H. So H, kinetic energy T, and potential energy V. If I apply a wave function on it, if I apply a wave function on this, what will happen? E operator psi. Now, on the kinetic energy, if you apply the wave function psi, kinetic energy in terms of operator you will write. First of all, what you will do? You will write it in the form of operator, and then you will apply the psi. So, kinetic energy in terms of operator, what it will be? P square upon 2m, and then you apply a psi. But potential energy V, it will remain as Vx, and you apply just a wave function psi. Now you can see E operator you know very well, P operator you know very well from the last slide. So can you get the Schrodinger equation here? Iota h cut del over del t psi, that is equal to P operator. If you apply h cut over iota, so that will become h cut square with negative sign upon 2m, and here you have del over del x, so here it will become del 2 over del x square psi plus Vx psi. Do you understand? So this is the Schrodinger equation. Now you can arrange it in any form, but this is the simple Schrodinger's equation, and this is simply a postulate. This does not have any kind of derivation or proof. This equation has no proof. It is simply a postulate. Okay, so do write this, then we will proceed. Very important thing. From here, if anybody has any doubt, you can ask. We'll move forward now, and we will discuss the time dependent Schrodinger equation from here. Time dependent Schrodinger equation. How to get that equation? Very important. So write the heading: time dependent Schrodinger's equation. So we have seen in one dimension the Schrodinger equation we can write as minus h cut square upon 2m del square over del x square. From here you can see this psi. Then you have Vx psi. Psi is combining of x and t, here you can mention. So it will be more easier for you to understand. And then you have also the term here with varying with time. So that we are writing in the other side. So here you have del over del t psi xt. Now you see very interesting thing that wave function is containing two different terms. One is varying with x, another is varying with t. So here you have psi x, and the time part t we can write separately. So that psi x denoting only the position, and ft here if I take as a function of time. So if I replace psi xt as psi x dot ft, then what the scenario will be? how we can get the simplified equation from here, and then how we can get time developed Schrodinger equation or time dependent Schrodinger equation. That will be very very important for you to understand many things which are upcoming in the sessions. Not in this class, in the further classes, this thing will help you a lot. In solving problem also it will help you a lot. So this I can give equation number 1. So from here, if I put the equation 1 in upper part, here we have minus h cut square upon 2m del 2 over del x square psi xt. Now I am mentioning as separate part of position and time. Vx, here you have psi x ft, and then here del over del t psi x ft. So here in this part, if you see, this is a derivation with x, so f of t will be a common thing, and this is a function of t here derivation, so this psi x you can take as common. So if I divide this whole equation by psi x f t now, okay, if I solve these things considering here t as a constant and considering here as a x as a constant, and then divide by psi x f t, what will happen, how this thing will change. So once I will also write this so that you will not get confused. Minus h cut square upon 2m, here x is a variable, so f of t can come out. Here there is nothing to change, to remain as it is, and here you have psi x can be taken out. So this is the format you are getting. Now if I divide it with psi x ft, then what will happen? This ft will cancel out and 1 over psi x will come. Okay, so here you can clearly see this thing is change as mentioned format, plus this psi x ft will cancel out, only vx will remain, and this side psi x will cancel out, so ft will remain only ft. Okay, so now you can see clearly that this side is depending only on x. You see, left hand side only x terms are there, and this side is completely independent of this side, depending only on the time. So these two sides are, you know, this LHS is depending on the x and RHS is depending on the time. So this factor, if this is equal to this, so obviously these are two different dimension thing, one is x, another is time. So we can take with another quantity, suppose E, that is both the things are equal to a common quantity which is E, suppose. So as you can see, the LHS is x dependent and RHS is your time dependent only. Okay, so now we will proceed from here in the next slide. Please do note down quickly. I will wait for you few seconds so that you can note down if somebody is writing it down. Okay, always write the things so that it will be beneficial for you at the end when you revise the things, and you will always have your proper notes with you all the time. So please share with your juniors, guys. Those as I'm seeing, all of you guys are, some of you are my previous students. So please share with your juniors because this is free for all There is nothing to pay or anything. So they can take the benefits of live classes also. They can obviously see the recording. You can send the link with them. So send it to your juniors as much as possible, or the classmates which those who are preparing for net exam and not yet done any full length courses. That is very important for them. Okay, so now we can separately write the things that minus h cut square upon 2m. Welcome Dipankar, how are you? Very good evening. So any doubt, any question you guys have, you can ask, and please share as much as possible so that more student can connect. You know. So if you see this psi x I have, if I multiply, so it will be minus h cut square over 2m del 2 over del x square psi x, and this will be multiplied with this, and this side we are considering e. So this psi x will also go with e. So e into psi x. So this you can see time independent equation again we are getting. Time independent Rundius equation we are getting here. I am also very good, Dipankar. Okay. And the other factor we are having is iota h cut del over del t f of t, that is equal to e. And here we have this ft, you see this ft, if I multiply in the other side it will be e into ft. So clearly you can see this we can solve with the integration. We can separate the variable del ft over f of t, you can take it this f of t here, that will turns out to be e over iota h cut, okay, dt. So now if you integrate both side, what we will get, this will be log of f, that is equal to, here if you integrate it will be minus iota e t over h cut plus a constant of integration log c, suppose. So then f of t, this function of t we need to calculate basically, that is the target, because we have this psi x t is equal to psi x ft. So f of t here we can calculate as c exponential of minus iota et upon h cut. Okay. So at time t equal to 0, we need to calculate this constant c. If we take t equal to 0, this c will turns out to be what? Only f of 0. C will be f of 0, function at when time it is 0. So this will lead out as f of t is equal to f of 0, function at 0 time, exponential of minus iota et upon h cut. This is a very important factor to remember. So now I can write here, we have good space. So here we have from equation number 1, if you see equation 1, what we have? We have psi xt as psi x f of t. So psi xt can be written as now as, you see psi x as it is, then ft is f of 0 exponential of minus iota et upon h cut. So this is a very important thing we are getting. So in the last session we discussed the bond postulate. Okay, so from bonds postulate, what do we know? The probability density. Probability density, how does this given? It is given as psi x square. If you remember from the last session, it is given as psi x, and if it is like psi xt, you can write it as psi xt. Okay, psi xt square you can also write, no problem with that. Complete thing, psi xt square. So from this, if we calculate, if we take this psi xt here as mentioned, and if we do the whole square of it with the value given here, so what it will turns out? It will turn out to be psi x f of 0 mod square only, or not. If you take exponential of iota et over h cut as a mod square, then its value will be just 1. Okay, that complex conjugate you have to take. So exponential of plus iota and negative iota will cancel out each other. So this is, you see, your wave function is time dependent. You see, wave function is what? Time dependent. But your probability density is coming as time independent. If this is the scenario, what you call it as? What you call this wave function psi xt? Do you have idea? Very interesting, conclusion come out from here, and this is a conclusion which could be asked in your net exam. From here you can get a question that your state is stationary or non-stationary. Here you see the definition of the stationary state, that if your wave function is time dependent, your wave function psi xt is time dependent, but the probability density, which is the square of psi xt, mod square of psi xt, that is coming out as time independent. And if this happens, then this psi xt is called a stationary state. A very important definition. So please do note down this. I will write the definition also. And when this stationary state will be non-stationary state, is there any example which you can give in the comment box quickly? Is there anything you can mention? Okay, so now you can write the definition. The wave function psi xt is time dependent. The corresponding probability density is time independent. Therefore, psi xt, which is a representing any state, a wave function, is called stationary state. Stationary state, a very important definition for stationary state. So do write this quickly, then we will proceed with an example where you can get a non-stationary state. Okay, and then how you get the non-stationary state? Non-stationary state will be when your probability density psi x t modulus square also is time dependent. Then your state will be a time dependent, and stationary state will now not remain stationary. Okay, so non-stationary state, anybody can give example in the comment box quickly. Those who all are watching, quickly comment down. Can you mention a particular example for a non-stationary state? If I take wave function psi x t as the linear combination of the two different function c1 psi 1 x t plus c2 psi 2 x t, what will happen if we develop time here? If we write the time dependent wave function from the Schrodinger equation, as you've seen, psi 1 x t will turns out to be exponential of minus iota e1 t upon h cut or not. Okay, c1 you can now write as a c star also, because of this f0 coming here. Not necessary, you can start it or c dash you if you want, otherwise we can keep it simple as c1. c2, if there is any doubt while writing this expression, you guys can comment, otherwise it's fine. I think easy for all to understand. This is e2t over h cut, okay, in the exponential. Because this is psi 2, this is psi 1, energies will be also different, e1 and e2, that we have to take care of. So if the energies are different and this is happening, in that case scenario, your probability function psi x t mod square, what it will be? So this you always write as psi star xt psi xt if you solve it. Okay, this is the basic thing to solve the probability density function to get psi square. I will also discuss this in very detail once we do the all other topics like harmonic oscillator and all these things. There it comes very frequently, and in all other problem solving also related to the wave function, you need to solve psi square very frequently. That is very important thing. So in that case, your psi star xt psi xt. So first of all, psi star, what is that? Psi star is simply the complex conjugate of this psi xt. So if you do the complex conjugate, you will basically consider iota sign change here. So minus iota will become plus iota. So I will not write the psi star here separately. You should understand that this thing will remain same, just a plus here and plus here will come, and then you have to multiply both these things. So what will happen if you do this? C1 psi 1 xt, if you multiply with the same thing here with the star, so star will become plus, so these will cancel out, and with that you will get just this. Similarly it will happen for C2. Okay, but what will happen? Okay, I can write this psi star if somebody is very new, like jam level preparing, then it could be difficult for you. So psi star will turns out to be C1 psi 1 xt exponential of iota e1 t over h cut. If somebody is not getting, I'm just writing so that so no one get confused. Psi 2 xt exponential of iota e2 t over h cut. This is the factor you are going to get. So with that, once you multiply this with this, you are just getting this factor. You multiply C2 psi 2 and this one, you are just getting this iota, and minus iota cancels out. Okay, but this is like complete exponential factor will cancel out. It's not like iota iota cancelling only. And once you multiply C1 with C2, or you multiply C1 psi 1 with this C2 psi 2, then what will happen? That is very interesting. So when you do the star complex conjugate, you also do C1 star and C2 star because of complex conjugacy. So here you get plus C1 C2 star Okay, then you have this psi 1, psi 2 star. Okay, you can mention this star also. Okay, here all this is basically just complex conjugate. Complex conjugate you are just doing here. So in that case scenario, C1 C2 star psi 1 psi 2 star. But here very important thing, that energies E1 and E2, they both are different. So in that case scenario, here you get exponential of minus iota E1 minus E2 t upon h cut. So this is not becoming, like 0 or something. So here there is a time factor coming basically. This is not time independent now. So similarly here you get C2 C1 star psi 2 psi 1 star here, and exponential of minus iota E2 minus E1 t upon h cut. So now it's not necessary that these two things will cancel out, okay, because energy is different. Also psi 1 star is happening, C1 star is happening here. So there is a very good possibility that these could be non-zero. So there is clearly time dependency in this factor, and if there is a time dependency in this probability density function, this is basically probability density. So if there is a time dependency in this probability density, this is just a non-stationary state. The psi xt is a non-stationary state. Is it clear to all? Okay, do write quickly, then we will proceed. Okay, so next very important discussion. This is basic discussion which will help you in solving the problems in between. Conservation of probability. So one important factor which is normalization. What do you mean by normalization? So if you have a wave function psi x or psi rt, its integration over the probability density psi rt or xt, probability density over the entire space x, here you can take from minus infinity to infinity, that should be what, as we discussed in the last session also, that should be 1. Or you can write in the complete volume psi rt in place of x in 3 dimension, in the entire volume psi rt mod square d tau, that should be 1. So this is basically called normalization condition. Normalization condition, very important. This is basically analogous to normal probability conditions, like you know very well that minus infinity to infinity px, this is basically px, probability density, dx, that should be what, 1, or you can say summation of all the probabilities, that should be 1. Conservation of probability always should happen. Okay, do write this. If there is any doubt, you can ask. Now we will discuss few other things which is very important, and to understand that, you know, wave packet, the phase velocity and the group velocity of the wave, why we need group velocity, okay, why can we have a single particle all along the space, okay, can a single particle travel all along the space without any other, can a single wave function travel all along the space, does it travel with the phase velocity, does it travel with the, you know, group velocity? These all phenomena we are going to understand now. So first of all, write this and then we will proceed to the next. Those who are joining newly, quickly comment down so that I can see who is just joined. Suppose a particle freely moving in x direction all over the space. If a particle is freely moving, what is the condition? Its potential energy will be what? 0 only. So then, what will be the Schrodinger equation? So from Schrodinger equation, we can get d2 psi over dx square plus 2m upon h cut square e psi, that will be 0. So here we can suppose that this factor 2me upon h cut square as key. So this is a differential equation. So what will be the solution of this differential equation? Psi x will be, from here this equation you can get a exponential of iota kx plus b exponential of minus iota kx in a free space. And you can get psi x as a sin kx plus b cos kx if your space is quite confined. Okay, it's not like infinite going, just a confined space. So this is very interesting. Okay, do write this quickly. So here you have a exponential of iota kx and exponential of minus iota kx. So this is what representing. Exponential of iota kx representing the positive going wave. Exponential of minus iota kx is representing the negative going wave. So in that case, now what we can have, exponential of iota kx is just a positive going wave and exponential of minus iota kx is negative going wave. So in that condition, for a positive going wave, if we write the operator p operator, p operator if you apply on this, what will happen? H cut over iota, del over del x exponential of iota kx. We have to solve this. So what it will be? H cut k, iota k will come out, but iota and iota will cancel out, so only h cut k, and here exponential will remain as exponential of iota kx. So what do we get? P value here, that is h cut k. But for negative going wave, what we will get? What we will get here? P operator, if you apply on exponential of minus iota kx, so that will turns out to be again h cut over iota del over del x, exponential of minus iota kx this time. So this h cut k will become minus h cut k exponential of minus iota kx. Just writing directly one step. So from here you can see that P is equal to minus h cut k. This is for negative going, and this is for positive going. Very important. So now do write this. Now we can have the wave function in other form, as we discussed earlier also. If we write the another way of the wave function, and then we will try to discuss the things for positive going and negative going, what will happen? Just do write this. So in another way, if I have wave function psi xt as psi x ft, and if I choose positive going wave, exponential of iota kx only, then our psi xt will become as a exponential of iota kx, and this energy factor minus iota omega t. So here you get a exponential of iota kx minus omega t. So now do you know the value of phase velocity here? What will be the Vp here? Omega upon k for positive going. Similarly, if you take negative going wave in place of positive, psi x will be, suppose another value b exponential of minus iota kx, just to change the constant values. So psi xt, what it will turns out to be, just similar to this b exponential of, here there will be minus iota in place of plus kx plus omega t here, and if this is plus omega t, what will be the phase velocity here? That will be as minus omega upon k for negative going wave. A very interesting thing. So now from here, if you have, there will be a lot of questions coming up, guys, in the next classes. Okay, these are the basic classes, initial classes, so you will get some theory portion. Okay, we should focus on the theory also, so that is why I am just not directly leading to the questions. You have to patiently wait for the questions to come up in the next sessions, as I am trying to give you a detailed course, not just like few practice session or practice question. So for that you have to be very patient also. So now what will happen, the probability density, okay, what will happen to the probability density of this system if you have, suppose, just a positive going wave now. So very interesting conclusion now. If particle moving in the x direction with respect to time, then as we discussed, the wave function will turns out to be e exponential of iota kx minus omega t. So there should not be a confusion with this. So what will be the probability density? That is psi xt square, mod square. So what it will be? Can you quickly comment down? If you do the probability density, it will be a square and exponential of iota kx minus omega t. You do the complex conjugate, there will be exponential of minus iota kx minus omega t. So exponential of minus iota with factor and plus iota with factor, this given kx minus omega t will cancel out each other. So we get the probability density just as a constant value. A constant value. It is not depending on position or anything. So if I plot position versus psi x square, the probability density, what kind of graph you are going to get, and what information you can interpret from this? If you plot this graph, what basically you are getting? You are simply getting a constant line, a square value. So the probability density is remaining constant with respect to time, with respect to position. It's just a square. Here it is a square, here and everywhere. Is it possible to have this kind of scenario? This is never possible for a particle to travel all along the space with same probability. This is not possible. So this is called wave is not localized. Okay, your wave is not basically confined to a particular space. It is moving along with the space with same probability, constant probability, which is not possible. So this wave this wave is not localized. Okay, so you can see that single wave cannot travel all along the space. So single wave cannot travel all over space. So then what to do? How we can overcome with this problem? That if it is not possible, then how this wave propagates? So the new concept, the new concept of wave packet, or you can say group of wave function with different wave number need to be introduced. Okay, so with the help of wave packet or the group of wave function, we can understand this, that how wave propagate. So the corresponding velocity. Now the velocity will not remain phase velocity. Corresponding velocity for wave packet is called as group velocity. It's called as group velocity, and this is denoted as Vg. Okay, So what is Vg? That we need to understand. So Vg is basically defined as d omega over dk. Okay, here you can write Vg is defined as d omega over dk. So wave will propagate now with the wave packet, and how the wave packet moves, you guys know very well. Its amplitude will change for a certain region, it will again reduce for a certain region, and it will again enhance, and this wave packet will move like this, and this covering the wave packet is called as envelope, and this velocity of this envelope, you can say also, is your group velocity. So this is a wave packet. Wave packet is not a single wave, it is basically the group of wave functions. Okay, so this is how wave packet or the group of wave function is introduced, and the group velocity needs to be introduced just to understand the wave, the particle movement phenomena. Because you see here, if I say a electron is here in this position, that same electron is here with the same probability, which is basically not possible. Okay, so the group velocity and the wave packet concept is introduced. To understand this further, now we will discuss the wave packet with group velocity and phase velocities. So I hope you understand that why we need to look into the wave packet instead of a single wave. This is very interesting. So from here, if you have any doubt, please ask. Sono Gore, you are joining quite late, I think. When you joined? Your comment is coming now. That is nice. So now, as we discussed, phase velocity. Yeah, it's all right, Sonu. No problem. So we have discussed a quite good amount of things. Yeah, I got it, Sonu. And the group velocity here is given as Vz, as we discussed, d omega over dk. Okay, so now we can have a relation between group velocity and phase velocity. So I will not be going direct like in much deep, because this is very basic things everyone knows. So I can write the relation between phase and group velocity. So we have Vz and Vp as mentioned here. So if I write Vz, which is d omega over dk, and Vp, which is omega by k. So if I simply write this omega as Vp into k, Vp into k, so in that case Vz will become d over dk Vp into k. So now we have to partially differentiate it. So from this we will get Vp plus k del Vp over del k. So this is the relation we are getting here. So we can clearly say that Vg is equal to Vp plus k dVp upon dk. This is the first relation we are getting. Okay, so in terms of lambda you can also get now. In terms of lambda you can also get. So how to get? K is connected with lambda as 2 pi by lambda. So from this we can say, if I write this dk, it will be as 2 pi over lambda square into d lambda with a negative sign. So this we can replace and we can get the value in terms of this. So Vg will convert in terms of lambda as Vp plus, you will put k as 2 pi by lambda, so that all you will do. And once you do and write this, you can do yourself, I think no problem, you will get much in this. So Vp minus, this will be changing with minus sign, and lambda dVp upon d lambda, that is the only change. Minus sign will come out and k will replace with lambda. If you calculate all these things, you will get just this. Okay, so these are the interesting relations. So here you can see Vg and Vp depending on on lambda and k. So there are two different medium. One is dispersive medium, another is non-dispersive medium. When you say a medium dispersive, when you say a medium non-dispersive, that is very important. If dVp over dk or dVp over d lambda is equal to 0, then medium is called non-dispersive. Right? And if the dVp over dk or dVp over d lambda is non-zero, then you will call it as a dispersive media. But this dVp over dk can be positive or negative. So then you will have a normal dispersion and a anomalous dispersion. Very important. So these two types we will also discuss now quickly. In the next slide, I have to move forward. So quickly going for dispersive media. If dVp over d lambda or dVp over dk is non-zero, but case number 1, if dVp over d lambda is positive, okay, so if dVp over d lambda is positive, then the group velocity will be less than phase velocity, and group velocity should be less than phase velocity, and that condition is for normal dispersion. Okay, but if your dVp over d lambda is negative, then group velocity will be more than phase velocity, and that is not a normal behavior of the medium, it is anomalous dispersion. Okay, so this is all very important things we just discussed. So from here we will lead to the next session. Okay, this will be the just last topic for today. In the next session we will continue the basic concept, very important. In the next session the probability current density will come, okay, and other continuity equation will also come. Lot of topics will come in the next session. So once I schedule the next session, I will let you know that when we will have a next session. So two continuous session we had. So now I will give you one thing, that you have to share this with your friends so that a lot of student can subscribe to the channel, and once a significant number of subscriber will be there in 1 or 2 days, more few subscriber, so more student basically joining, then we will have next session. So till then you guys please share these sessions with your friends. As soon as you share these sessions, more student will come, and our topic will reach to the maximum number of student. Okay, so I hope you enjoyed this session, and this session will continue in the future also, okay, free of cost for all of you guys. So I hope you enjoyed a lot of things here. So this is the lecture 2, just now concluding it. If any doubt you can always ask. Next session we will have very soon. So till then, take care, good night, see you in the next session.